Hello everyone, I am Mona Narmani. Welcome back to my channel and welcome to C Programming for Beginners series. This is the part 7 of Operators in C, where we'll be studying about bitwise operators. The video link to part 1 to part 7 is given in the description box. Do check out. Let's start with bitwise operators. The bitwise operators are used to perform bit level operations on the data. Therefore, it is also called as bit level programming. Here bit stands for binary digits 0 or 1. Bitwise operators are mainly used in numerical computations, which makes the calculation process faster. In arithmetic and logic unit, that is ALU, within CPU, mathematical operations like addition, subtraction, multiplication, division are done at bit level. Decimal values will be converted to binary values, which are the sequence of bits, zeros and ones, and the bitwise operators work on this sequence of bits. It is mostly used in integer data type. This was just a basic introduction of bitwise operators. Totally, there are 6 bitwise operators in C. Those are bitwise AND, bitwise OR, bitwise XOR, ones complement, left shift and right shift operators. The truth table of bitwise AND, bitwise OR and bitwise XOR is as follows. Bitwise AND results into 0 when both the bits are 0 or either of one bit is 0. Bitwise AND results into 1 when all the bits or both the bits are 1. Bitwise OR operator results into 0 when all the bits are 0. If any one of the bit is 1, then bitwise OR will result into 1. Coming to bitwise exclusive OR. Bitwise exclusive OR results into 0 when both the bits are same. That is, when both the bits are 0 or both the bits are 1, then exclusive OR will result into 0. Exclusive OR results into 1 when both the bits are different. That is 0, 0, 1 or 1, 0. When both the bits are different, exclusive OR results into 1. Let's look at each of these bitwise operators in detail. Let's start with logical AND, but before that, the bitwise logical operators work on data bit by bit. Starting from the rightmost bit, which is called as least significant bit or LSB, working towards the leftmost bit called as most significant bit, MSB. Coming to bitwise AND operator, the logical bitwise AND operator is denoted by a single ampersand symbol. As already seen in the truth table, the result of bitwise AND operation is 1 when both the bits have the value 1, otherwise the result is 0. That is, if any one of the bit is 0, the bitwise AND operator results into 0. Let's take one example where A is equal to 6 and B is equal to 14. Its binary equivalent of 6 is 0, 1, 1, 0 and binary equivalent of 14 is 1, 1, 1, 0. Now suppose if we want to perform bitwise AND operation on this A and B. So that is denoted as A single ampersand, which denote bitwise AND B. So we get the result as 0, 1, 1, 0. How we got this result is apply the truth table of bitwise AND operator on bit by bit. 0 and 0, the result is 0. 1 and 1, the result is 1. Again 1 and 1, the result is 1. 0 and 1. So when any one of the bit is 0, the answer is 0. 0 and 1, the answer is 0. Now convert this result 0, 1, 1, 0, it's equivalent to 6. So this is how the bitwise AND works. Coming to bitwise OR operator, it is denoted by this single vertical bar. The result of bitwise OR is 1 if at least one of the bit is 1. The result is 0 if both the bits are 0. Again, considering the same example, A is equal to 6 and B is equal to 14, converting it to a binary equivalent and performing bitwise OR operation. So bitwise OR operation denoted like this. So we get the result as 1, 1, 1, 0. So 0 or 0, 0. The answer is 0. We know with the truth table of bitwise OR. 1 or 1, the answer is 1. 1 or 1, again the answer is 1. 0 or 1. So with the truth table of bitwise OR, we have seen that if any one bit is 1, the resultant of a bitwise OR is 1. So 0 or 1 is 1. So again convert it back to a decimal form. This is equivalent to 14. So when you perform A bitwise OR P, the result will be 14. Similarly, coming to bitwise exclusive OR. So this XOR is a shorthand form. It is called as exclusive OR. Bitwise exclusive OR, it is denoted by this caret symbol. The XOR results into 1 if both the bits are different. If both the bits are same, then the result is 0. So this we have seen with the help of truth table. Now let's look at the same example where A is equal to 6 and B is equal to 14 and try to apply bitwise exclusive OR. So when we apply A XOR B, we get the result as 1, 0, 0, 0. Again 0, 0. Both the bits are same, 0, 0. Therefore, the exclusive OR will give the result as 0. 1, 1. Again, as per the truth table of exclusive OR, when both the bits are same, the result of exclusive OR is 0. Hence, 1, 1, 1 XOR 1, the result is 0. Again, 1 XOR 1, the result is 0. 0 XOR 1. So when both the bits are different, exclusive OR will give the result as 1. So hence 0 exclusive OR 1, the answer is 1. When you convert it back to an decimal form, this A XOR B is equivalent to 8. The next operator is bitwise complement. So this bitwise complement is also known as ones complement operator, and it is represented by this symbol, tilde symbol. It is a unary operator which works only on one operand. This bitwise complement operator is a unary operator, which means it works only on one operand, not like the other bitwise operator which requires two operands. Bitwise ones complement operator flips the bits. So flips the bits. What does it mean is it changes 1 to 0 and 0 to 1. So if there is a bit 1, that when you apply complement, it will become 0. And if there is a bit 0, if you apply complement, it becomes 1. So that is, it flips the bits or it inverts the bits. The next one point you need to remember here is for any integer n, bitwise complement of n will be minus of n plus 1. Let's take an example of bitwise complement. Suppose A is equal to 6, its binary equivalent is 0, 1, 1, 0. So suppose if you apply bitwise ones complement on this A, denoted as this bitwise ones complement operator tilde A, we get the result as 1, 0, 0, 1. So how we got the result as 1 is 0. As per bitwise one complement, 0 will be flipped to 1, 1 will be inverted to 0, 1 inverted to 0 and 0 inverted to 1. Now this is equivalent to the ones complement is of 6 is equivalent to minus 7. So how we get this minus 7 is, remember that last point, for any integer n, bitwise complement of n will be minus of n plus 1. So here we have an integer n, that is 6. So bitwise complement of 6 will be minus of n plus 1, minus of 6 plus 1. So that is nothing but minus 7. So how we got this minus 7? To explain this, I will make another video explaining in detail how the bitwise ones complement work. So till then, just remember that for any integer n, bitwise ones complement of n will be minus of n plus 1. Next comes the shift operators. There are two shift operators in C programming, left shift operator and right shift operator. We'll start with the bitwise left shift operator. Bitwise left shift operator is denoted by this symbol, two less than symbols. The syntax of bitwise left shift operator is as follows: operand left shift operator n. So here operand is an integer expression on which the shift operation need to be applied, and n indicates the number of bits to be shifted left. Left shift operator shifts the bits to the left side, and the number of times bits need to be shifted, that is specified by this n. N bits will be shifted on the left side, and when we shift bits to the left side, on the right hand side there creates an empty space. So that right hand side empty space will be filled with zeros. Let's take an example. For example, A is equal to 6. Its binary equivalent we have seen 0, 1, 1, 0. Now suppose if I want to perform A left shift 2, which means I want to shift A 2 times to the left side. Shift A, that is 0, 1, 1, 0, 2 times to the left side. So that is what it indicates. How this is performed, let's check it out.
Bitwise left shift operator. A is 6. We want to shift this A 2 times to the left side. So let's check how it works. We have considered, let's consider it as a 8 bits. So this 0 will be popped out. 0 will occupy this place. Shift 1 time to the left. Shift to the left. Same thing happens for all the bits. Now this space is left blank, so here 0 will be inserted. So this is the result after first shift. After first shift. Now if you convert it to a decimal, so this is equivalent to 12. But we need to shift it 2. The n value is 2, so we need to shift it 2. So we need to perform one more time left shift. So this bit will be popped out. This will come to here, the MSB position. Similarly, go on shifting it. Now again this place is blank, 0 will be inserted. So this is the result after the second left shift. So this is second shift. Operand left shift 2 times. A should be shifted left side 2 times. So this is the result after second shift. So this decimal equivalent is 24. So this A is equal to 6. After performing 2 times left shift, its result is 24.
Coming to the last bitwise operator, that is bitwise right shift operator, which is denoted by this symbol 2 greater than symbol. The syntax is as follows: operand right shift operator n. Again, operand indicates an integer expression on which the shift operation need to be applied, and n indicates the number of bits to be shifted right. Right shift operator shifts the bits to the right side, and the number of bits to be shifted is specified by this n. In a right shift operator, n bits will be shifted on the right side, and when we shift the bits on the right side, on the left side an empty space will be created, and those empty space will be filled with the value 0. For example, again let's take the example of a same 6. Now suppose if we want to shift 6 to the right side 2 times, how that is performed, let's check it out.
Coming to bitwise right shift operator, A is 6 and we want to shift this A 2 times to the right side. Again considering it as a 8 bit, so this 0 will be popped out, 1 will come to the LSB position. Similarly, shifting it to the right side. In left shift, we are going to shift the bits to the left side. In right shift, we are going to shift the bits to the right side. Now this position is left blank, so 0 will be inserted. Now when you convert it to the binary form, this is 3. It's equivalent to 3. So this is the result after performing first right shift. But we want to shift it 2 times. Again perform one more time. So this 1 will be popped out. 1 will be shifted here, 0, and so on for all the bits. Now again this position is left blank, so 0 will be inserted. So this is the result after performing second right shift. This is equivalent to 1. After second right shift, this is equivalent to 1. So A is equal to 6. After performing right shift 2 times, its result will be 1.
Lastly, let's check the precedence and associativity of bitwise operator. So the highest precedence goes to one's complement and its associativity is right to left. The second precedence or the second priority is given to left shift operator and right shift operator and its associativity is from left to right. The third precedence goes to bitwise AND operator whose associativity is left to right. Fourth preference or fourth precedence goes to exclusive or bitwise exclusive OR operator. Again, its associativity is left to right. Fifth precedence goes to bitwise OR. Again, its precedence is left to right. So, what is this precedence? What is this associativity? Again, it holds good even for bitwise operator, whatever we had studied in the previous videos. The same thing applies here. One's complement has the highest precedence. Second goes to left and right shift operators. Third to bitwise AND. Fourth precedence to exclusive OR. And last fifth precedence to bitwise OR. And again there is bitwise assignment operator. In assignment operator we have seen a shorthand assignment operator. In the same way we can also apply these assignment operators to bitwise operators. So that can be applied to bitwise AND, bitwise XOR, bitwise OR, left shift and right shift operator. And the precedence for this is the last precedence 6 and its associativity is from right to left. Next, let's understand all these bitwise operators through a program. Whatever the examples we have seen, we have discussed in this video, that let's check it out through a program. So this is the program written for all the bitwise operators which we had discussed so far. For the value a is equal to 6 and b is equal to 14. Let's execute and check the results. So we are getting the same results even in the program. That's all in this video. I hope you have enjoyed this video. Do like, share and subscribe for more such videos. Thank you.